This is the last section in Chapter 4. Here's where we take your systems of inequalities and show some real applications. This is something that I certainly used in my career, solving problems using linear programming. So, and linear programming, you're going to find out shortly, is simply using systems of inequality. Now, why are those so useful to us? Because almost every problem we want to solve involves a limitation or limitations on resources. I mean, one of the ones we are all very aware of is money. So it may be money, it may be space, it may be time. We all know that inequalities are often coming into play here. We have a certain amount of dollars. You know, we can spend up to some limit, perhaps, to establish a business or something. And we may have other limitations too, like the amount of space. And once we get more than one variable, that's when we get into a system, when we have more than one resource that we're paying attention to. So we're going to start just by reviewing what we learned about graphing a system of inequalities. You can skip over this if it's all very evident to you. We'll start with this first one. I'll do it in blue. We're going to graph this system, and you remember that I like to transform this into slope-intercept form, particularly for inequalities, because then I can use this symbol to help me understand which side of the boundary line I am going to be shading. So I subtract x from both sides. That's my boundary line. Let me draw it. So I am anchored at my y-intercept here at +3. So we know that point's there. And then what is my slope? Down 1 over 1. Down 1 over 1. Down 1 over 1. Down 1 over 1. So here we have this. Let me draw the line now. Draw the line right through there. And the reason I'm keeping it in the first quadrant is because I noticed over here that I'm only going to be using positive x's and positive y's. Let me draw those lines right now. X is greater than 0. Draw a green line for that. So here's x is equal to 0. And then we've got y is greater than or equal to 0. So I'm going to draw that boundary of y is equal to 0. There it is. Now I'm just going to put in those little arrows to remind me which side of each line is my solution. This one, y was less than, so remember I'm looking down. So there's my solution space, and I can color that in. This is the place where all of these inequalities overlap. That's an important element of systems of inequalities. It's where they all overlap. Graph the system of inequalities and find the vertices. Okay, so let's go for finding the vertices. It seems to me fairly simple, isn't it? Here we've got one vertice at 0, 0. I've got another right here, which is at 0, 3, and still another here at 3, 0. So these are the vertices of my solution space. Now we're going to actually practice this. We're going to imagine that Mrs. Wood has a biscuit factory. You're going to see it's not much of a factory, but anyway, she has a biscuit factory where she makes two types of biscuits. Jumbos. Okay, so we've got jumbos. And we've got mini mints. So, mint biscuits. Oh, sounds disgusting. So, jumbos and mini mints. These are her two outputs that she could have. And a problem is going to be, how should she allocate her resources in order to make the greatest income? Now notice we haven't asked about profit. We've asked about income. So all I have to know is how much she's going to get paid for each. Let's read down through the problem. The oven can bake up to 200 biscuits a day. Okay, so this is a constraint. The oven constraint. You can't go over 200 biscuits a day. So if maybe I should shortcut this a little bit. I'll call this M. Whoop. I'll call this M. Well, that didn't work. And I'll call this J, just so we have nice variables we can use. I'll go back here and write my M again. 200 biscuits a day. So I could actually do 200 jumbos, or I could do 200 minis. I could do, it seems, 100 of each, right? So any of these combinations I could do. Now I haven't written an inequality, although I could, and I will. What I'm doing right now is I'm drawing a boundary line for the information that I just read. The oven can bake up to 200 biscuits a day. Now, without even thinking about what the actual equation or inequality is, I know that my solution space is going to be less than, right? We said we can't go more than that. Up to, not exceeding. So let's see what that would look like if I wrote it out. Jumbos plus minis is less than or equal to 200. And in graphing this, I would say M less than or equal to a negative J plus 200. And you will see that in graphing my boundary line, I anchored myself right here at M being 200, and I had a downward slope of negative 100 over 100. That's the same as negative 1 over 1, isn't it? We're coming up against another constraint, and this constraint is going to be flour. She only has 300 ounces of flour. Each jumbo that she bakes takes 2 ounces of flour. Each mini requires 1 ounce of flour. So what would my inequality look like? Well, it's going to be less than or equal to 300, isn't it? And we're going to say 2 ounces for every jumbo plus 1 ounce, which we don't bother writing, for every mini. And when we add those up, it's going to be equal to 300. So let me see, what would my boundary line look like? I'm going to put this into slope-intercept form. Negative 2j plus 300. So for this one, I've actually got my point up here, right? This is my, I was going to say y-intercept. In this case, it's my m-intercept. And my slope is down 2 over 1. So I'm going to go down 200 over 1, and I end up being right here. Let's try drawing a line again. Let's see. So from this down to here, right there. Does that look about right? Okay, on this one as well, we know that we're talking about staying underneath this, less than this. So the place where we overlap right now is this corner right here. What other constraints do we have? None. Okay, so those are the only 2 constraints we have to worry about. The oven, which has a capacity constraint, and the flour, which is a constraint on the amount of materials available. What did we say she was trying to do? She was trying to earn the greatest possible income. Whatever the objective is, the goal, that's going to be expressed as an equation in our objective quantity. The income from jumbos, the income from minis, we're somehow going to put that together to figure out how to get the greatest income. So our objective quantity we're going to express as an equation. You'll see how we're going to use this in a minute. My income, well, Mrs. Wood's income, equals, now notice we're in cents, not dollars, but that's because I prefer integers to decimals. Just have to remember that we're in cents when we get to the end, because we don't want to talk about, I hope, we don't want to talk about her income being in cents. That would be so pathetic. So she gets 10 cents for every jumbo, and she gets 8 cents for every mini. Now, one of the things that's clear is we're not going to have any negative here. So we can say we're only operating in the first quadrant. We know we're not going to have negative biscuits of any kind. I could, at this point, and I will, go fill this in for you. So we're talking about this space right here. This is where these 2 systems of inequality, the 2 constraints, the oven and the flour, this is where they overlap. So she's got a lot of choices here. Everything in the green space is a choice available to Mrs. Wood. She wants to maximize her income. Why wouldn't she? Of course, she's in business. And she can do that in all these ways. Well, there are some ways that we can pick out immediately that wouldn't make any sense at all. So we can eliminate that corner, 0, 0. But these others are viable places, and here's the clue. Here's why we love linear programming. The maximum and the minimum of the objective quantity will be found at the vertices. So we are most interested in the vertices. This is why we've been talking about them. So where is she going to find the greatest? We know it's not here, but maybe it's here or here or here. So where is she going to make the most money? We're going to use these points in this way. We're going to test every point. I'm not going to test 0, 0. I suppose I could, but if I put 0 in for J and 0 in for M, what do I get? Right, 0. That's so each one of our points looks like this, doesn't it? JM. I'm going to try this one, which is 0, 200. And I'm going to try this one, which is 100, 100. Now what am I testing here? I'm testing the vertices. And here it's, let's see, 150. 150 and 0. We will now put in these point values 10 times 0. So we eliminate this, and it's just plus 8 times 200, or what's that? 1,600 pennies, or $16. Income on this one would be 100 times 10, or 1,000 pennies, plus 800 pennies, or $18. And the income from this one would be $15. So clearly, linear programming can help Mrs. Wood determine how she should use her flour and her oven capacity. She should use it in this way. In order to maximize her income, she'll want to go to this. This is the sweet point for her. Let's just talk about linear programming in general now. How is the objective quantity used in a linear programming problem? You look at what your goal is. If it's income, like in the case of Mrs. Wood's factory, how much income are you going to get from each jumbo, plus how much income are you going to get from each mini? How is the system of constraint inequalities used? Well, that's actually how we put together our boundary lines and figure out which side of the boundary line is our solution space. So this, whatever resources that are limited, those are the ones we're going to put in as constraints. In a linear programming problem, which ordered pairs should be tested? You know that. We're going to test the vertices, because it is at the vertices that we will find our minimum and maximum values. What are the vertices of the feasible region? Okay, the feasible region, if you see those words, that's just the solution space. That's where it is feasible for, in our previous problem, for Mrs. Wood to bake. I mean, she could have done, like right here, 25 of each. Now, she wouldn't do that unless she was not feeling well and could keep up the pace. She's really trying to maximize. She'll go to her limit. And that's what we're going to do here. We go to our limits in order to maximize, or minimize. The vertices that we find at those limits are, let's see, 0, 0. Clearly that's going to be a minimum. And then we've got 0, 3 in this problem we're looking at on this page. And we've got 2, 4. And we've got 4, 0. So our minimum and our maximum are going to be found in these 4 points. Let's figure out what those are. Well, the minimum is pretty easy for us to figure out. There's no negatives here, so I know my minimum has got to be at 0, 0. That's going to be my minimum, because at 0, 0 we're going to have C, our objective quantity, equals 0. The more interesting question for us, because it's a little more difficult, really, the difficult ones are the interesting ones, is what is the maximum? If I go with 0, 3, what do I get for my C? It would be nothing for this, and C would be 21. How about 2 and 4? What will C be equal with 2 and 4? 10 plus 28, or 38. And what will C be if I go for 4 and 0? Well, we can see now what our maximum is, can't we? Because if this is 0, my C is equal to 20. So this one is not my maximum. This one is not my maximum. This one is. Using linear programming. Here are your rules, what you do. Develop your objective function. So when you read your problem, what is it we're trying to do? Are we trying to maximize income? Are we trying to minimize time? Whatever it is we are interested in, we're going to have an equation. When we say objective function, that's an equation. And that's where we're going to test our vertices. Then, system of constraints, here are our inequalities. And that's where you're going to determine your feasible region and your vertices. So when you get your feasible region, the vertices are going to be used back in this equation. So first, develop that equation, your objective function. Second, use your constraints to find the feasible region. 3, identify the vertices. Remember this, because so far our vertices have been pretty obvious. They've been right on the grid line, so they were easy to read. This is not always the case. So you may have to use a linear system to find out where the two boundary lines are intersecting. Getting complicated here. The fourth thing you do, once you know what all those vertices are, is you test them for either the minimum, if that's what you're looking for, or the maximum. So 1, 2, 3, 4, and you will have a good solution for your problem of trying to get the best result with limited resources. Boy, doesn't that sound like real life.